have finished the first chapter in the saga of this semester on linear algebra. You are not done with linear algebra yet. In fact, you've hardly started. But we're going to use it for stuff. And the first thing we're going to use it for is something for which it's just eminently suited to allow you to do something you might have taken in another class at some point in your lives, if you took stats in particular, but to understand it in a very different way, because the underlying math is all linear algebra. And that's linear regression. So we're going to talk about regression, and we're going to start slow. We're going to start with a really trivial case that seems even more trivial than you imagine, and build up the concepts for it, and then generalize. And in doing this, we're going to have vectors and matrices again. But now we're thinking of them not as just these objects that we do these abstract things on, or as these points in space that we're understanding the geometry of, although we will use that. Now we're thinking about linear algebra as a tool for understanding data. So we use linear algebra to understand models. That's how we develop the concept of a matrix in the first place. Is we have a model of a box. It takes numbers in, spits numbers out, and we assert that it's linear. And if it's linear, it turns out that that box can be completely described by its impulse responses, and that, if you line them up and make them columns of a matrix, then it can be described as a matrix multiply. That's how we got to linear algebra, and then we spun some things about how to understand what that system might be doing by understanding what its range space is, so where does it reach and where in the output space does it not reach, and what its null space is, what things that you put into it are closhed, okay? And the SVD gives you both of those, right? So the S matrix, the diagonal matrix, tells you which dimensions in the output orthogonal transform you can reach, and the zeros in that matrix tell you which dimensions in the input matrix get lost. So that's a summary of everything we've done so far. But what we're going to talk about now is using linear algebra not as modeling a system, but as understanding some data you've collected. So when you collect data, so here's some data, and it consists of two numbers. One is x that you controlled, and one is y, which you measured, say. So x is an independent variable in some experiment, and y is a dependent variable in some experiment. So x could be the amount of some supplement that you fed a rat, and y could be its change in weight across a week of living on that amount of that supplement. And your notion is, the more I give the rat this stuff, it's going to get fatter. Okay? And you want to say, is that really true? And if so, you know, what's the weight gain per gram of this supplement? Or something. I made that up. You can make another example you like better. Okay? And so you have various conditions that you ran, and for each one, you have a result that came out. And I had stated this in terms of weight gain. I was clever about that without realizing I was doing it. Because this dumb example we're going to start with, linear regression, do those data, are they well described by a straight line? But in particular, by a straight line for now, that goes through the origin. It's not just any straight line. So if you learned about linear regression in some stats class, you just want to fit a line to it, whichever line fits it best. For now, for the first half of this class today, that line will go through the origin. So all we're saying is, you know, the y's, I'd like to predict them based on the x's. And I'd like to predict them as well as I can with a line that can go through the origin. So it could be this line, or this line, or this line, but it's got to go through the origin. And for the example I just gave you, if I don't give you the supplement, your weight shouldn't change because I haven't changed anything about you, so our model is that it goes through the origin. So we're going to stick with that for now. Okay, and we're going to do that by measuring the mistakes that any given line makes. So here's a bunch of the mistakes, and we're going to say, I'd like the mistakes to be small. Now, I can't just take the mistakes and add them up and say, that's my measure of how big a mistake I made, because you notice some of the mistakes are the data's above the line, and some of the mistakes, the data's below the line. So if I added my mistakes up, you know, this error and this error would cancel. I don't want that. I just want these things to be close to the line. So I have to do something to turn all these negative numbers positive. And there's lots of things you could do. You could take their absolute values, you could square them, you could cube power. You could raise them with any power you like. You could do something that's not a power, put it through some function. We'll in fact talk about that next week, maybe the week after. So there's lots of things you can do about what's your metric for error. But the idea is I want to take a line such that that error is minimized. I would like to have a best fitting line, and I like to think about where that line comes from. So that function of take each measurement that I made, predict it by each independent variable that went with it that I had done as an experimenter, and I want a straight line to the origin, so that means the x thing gets multiplied by some number. I don't know what the number is, and I'd like to estimate it. Okay? I'm going to say, how different are these by squaring them and adding them up? So I'm going to be minimizing squared error. Now, the form of that equation is already kind of looking like linear algebra, like something you've done before. And so we're going to utilize your expectations and understandings of linear algebra in order to solve this problem. But again, let's look at what happens before we start solving it. Should we turn this one off?
Somebody takes light off the board, but we can.
Oh, okay. I don't know which is better. It just seems kind of glaring. That seems better to me. Is that better in the back in terms of using the board, which I have written on?
I don't think it
Is
matters
this still
so much.
visible?
It's dimmer. It's hard
Whatever.
to read.
Whatever you guys like. All right. So suppose we got a whole bunch of data, a lot more than I showed a minute ago. Okay? And here's a possible line, and it obviously doesn't fit it very well. So I take all these errors, I square them and add them up, and I get some number. Now what happens as I rotate that line around? So here it is rotated, the error goes down, rotated some more, the error goes down some more, and that looks like a pretty good one, because now I've rotated some more, and the error's starting to go back up. And as I rotate the other way, obviously the line doesn't describe the data very well, and the errors go up. And so there's a couple things to see here. One is, it looks like there's a bottom. That's good. We wanted to have a best fit. It'd be nice if things are all set up such there's one beta that's the best one. And it looks like that works well. Now, that picture of the error that happened as I just rotated that around looks like what kind of function? A quadratic. Why does it look like a quadratic? Well, no, I know it. Why? No, I'm saying why does this look like one? What is it that caused it to look like a quadratic?
Because it defined it.
Because we have an error function that's a quadratic. So of course it looks like a quadratic, and of course it has a bottom. Okay, when the derivative goes to 0, it could be a top, a maximum rather than a minimum, but this is a sum of a bunch of positive numbers which you go way out are going to go up. So it's going to have a minimum. Okay? Now because it has a minimum, there are a variety of ways of solving this, saying where is the minimum? Okay? So one way is to go back to high school calculus and say we'd like to find a minimum. So in this equation, if we're trying to find a minimum, what numbers in this equation are constants, and what number is the variable that we're going to vary to minimize? So what's obviously a constant here? It's not going to change. Y and, yeah, the y's and the x's are the data. We already have them. We're not changing the data to see what minimizes. The only thing we're changing is beta. So this is just a function of one variable. This is calculus the first month. Okay? So we have this equation, which is the sum of sum over I. Write it the same way as there. Write it the same way there. N, yn minus beta xn squared. That's the same as that thing. This one's kind of different. Okay? So I'd like to minimize that. So to minimize that, when you get to the bottom of that valley, it's flat. Otherwise known as its derivative with respect to the x-axis, and the x-axis in that plot was beta. So its derivative with respect to beta is 0. So I'm going to take the derivative of this with respect to beta, set it to 0. That's what you did in calculus to find a minimum or maximum, and solve for beta. Okay? So let's do that. Now, this is the derivative of a sum. And one thing you learned in calculus is that you can rewrite this as the sum over n of the derivative of what's inside the sum, yn minus beta xn squared d beta. this back in early calculus, if you remember taking it. That means the derivative is what as an operator? Something we're spending our semester talking about. The derivative itself as a thing that acts on stuff is fill in the blank. Linear. It also follows. This is superposition. It also satisfies homogeneity. The derivative of 5 times a function is 5 times the derivative of the function. It does exactly the rules of linearity. The derivative is linear. And if you remember it, integration is linear also. Integration being linear should be obvious because integration is a sum. So of course it's linear. Okay. All right. So now we're taking this derivative. At least make this visible. Okay. So this is a derivative of a quadratic. So it's 2 times the stuff inside. Oh, let me not forget my sum. Times the stuff inside. Beta. Oh my God, where'd my x go? There it is. Beta xn times the derivative of what's inside. Okay, I want to take the derivative of yn minus beta xn. Yn is a constant. What's the derivative of a constant?
0.
What's the derivative of minus beta xn with respect to beta? Minus xn. Okay? And this still equals 0. Now, let's multiply it out. Well, first of all, let's get rid of the 2. I'm going to divide both sides by 2, so the 2 is going to go away. I don't care about the 2, so I'm just getting rid of it. Right? You can divide by 2, that 2 goes away. Divide 0 by 2, that goes away. Okay. So I can get rid of the 2, and then I'm going to multiply out what I got. So I've got a sum over n of yn times minus xn, so that's negative yn xn. And then I have a plus, because minus times minus is plus, beta I'm now going to pull out, the sum over n of xn times xn. Okay? It's just algebra. What's the first thing there? Forget about the minus sign for the moment. What's this? Looks awfully familiar. You see this a lot. It's a dot product. Okay? So now this equals minus y, treat it as a vector, dot x, treat it as a vector. And before I get to the second term, let me clarify what we're saying. We have a data set. It's a bunch of x, y pairs. But now I'm going to call them vectors. Here's y, the vector. y1, y2, yn. Here's x, the vector. x1, x2, dot, xn. So each corresponding element as a pair is my data. This was my independent variable, this was the resulting measurement. This was my independent variable, this was the corresponding measurement. So I'm just taking my data and just labeling it like it's a vector. Okay? So this is minus y dot x. What's this thing? X what? This is the sum of the xi's times themselves. So it's the sum of the xi's squared. What is that object? Number 1, it looks like a dot product. This time x with itself, but we have another name for that. Square its length. Give that woman a Cupid doll. Length of x squared equals 0. Okay? We're basically done. We want to solve for beta, so we're going to move this to the other side. And now we have beta times that. We're going to move this to the other side by dividing. And the net result is that beta equals x dot y over the length of x squared. Okay? We have our answer. This is how you fit a line through the origin. And we're done. Now, that was all symbol pushing. It was all, yeah, you know calculus, and we have this thing we want to minimize, so take the derivative, set it to 0, do all the work, turn all the crank, and we have a nice answer.
You may have said this already. Where did the 2 go?
Yeah.
So this is 2 times a bunch of stuff. I pulled it out, because 2 times everything, and if 2 times something equals 0, then the something equals 0. So I just threw it away. Other questions? data, we said let's fit it, and fit it means minimize this error function. So I wrote down the error function, took its derivative, set it to 0, and turned a crank and got some weird equation. So that's not very satisfying. For those of you who like math and algebra, you know, we took a problem and we solved it. Fine. But what does that mean? So there's another way to look at this that is much more intuitive and uses the geometry that we've been talking about that. So we solved it here. Oh, I should have switched to the slide at some point, saying, you know, here's my y vector and here's my x vector. And sitting in that error function was my y vector minus beta times my x vector. That already sounds like something that you would have a geometry for, because y is pointing in some direction, x is pointing in some direction. We're stretching it and then saying how different are they. So now we're going to look at that as a geometric thing. Now understand that back when I drew the original data, so I'll just draw an inset of what was on the slide a bunch back, where I had a bunch of data points. They were in a space where the x-axis was x and the y-axis was y, and these were x-y pairs. That was the raw data we started with. And that's a space that's only got two dimensions. There's one independent variable, there's one dependent variable, and there's dots on there, but each dot is lying in a two-dimensional space. We're now moving to thinking about this problem in a very different way. We're now in a space that is as dimensional as the number of data you've collected. So the y vector is not a one number, it's n numbers. So it lives in an n-dimensional space where the first dimension was the first data point, and the second dimension was the second data point, and the third dimension was the third data point. It's a very different space we're living in. But in that space, we've got a y vector that we'd like to account for, and we'd like to get beta times the x vector to be close to it, meaning we'd like their difference to have a short length. Length squared, actually, right? Because we're taking, where do I have the equation? Well, forget about the derivative part. We're taking this vector, and we're taking its squared length, and saying, make the squared length small. So that means we can think about it in linear algebraic terms. So let's do that. So now we're in that n-dimensional space, not in 2D at all. We're in some complicated, I can't perceive it, n-dimensional space. I collected 100 data points. There's 100 dimensions. For the x vector, the values on those dimensions are the independent variable for the first data point, the independent variable is the second data point, the third, the fourth. That's the vector for x, which is written as a column over there on the left. And there's a vector for y. Now, I'm going to take the x vector, and I'm going to multiply it by a constant, which means I'm going to take the x vector, make it longer or shorter or possibly point it in the opposite direction. That's all I can do. I'm saying, where along the line defined by the x vector am I closest to the y vector? And so one way to think about that is if I affixed a rubber band to the y vector, wrapped it around this big x line, and let it go and say, go to where your tension is smallest. It would go right here. It would go where the error is perpendicular to the x vector. If I go over here, it gets longer. If I go over here, it gets longer. Why? Because if I put it over here, let me draw it over here. So I'm just replicating what's over there. Here's an x vector. Here's a y vector. Okay? And somewhere there's a perpendicular. But if I went somewhere else that wasn't perpendicular, say here, so I make beta bigger, for example, here's the new error. And the new error is made out of a right triangle with this plus this error, which means that the hypotenuse is longer. So the hypotenuse is minimized when this part is 0. Okay? So that's just a way of proving what seems, intuitively true, which is you minimize when they're perpendicular. Well, we know what perpendicular means, right? So we can just write out, I want this to be perpendicular. So here was the answer we got last time, but now let's do it with the intuitions we have for linear algebra. And so the intuition is you want the error to be perpendicular to those points that can be reached by the input. Okay, x is the input, y is the result. And so you'd like the error to be as close as possible. So what do we mean by that? So we want beta such that the error, beta, such that, st, such that, x stretched out by beta compared to y, I guess I should write it in the way we've been writing it. I almost knocked it over, but I didn't. So y minus beta x, we'd like that to be perpendicular to x. That's what we want. This is the error vector for any given beta. You take x, stretch it out by beta, that's a vector. You take y, you subtract them, that's this thing. And we'd like that thing to be perpendicular to this line, so we'd like it to be perpendicular to x. So now let's do some linear algebra. The first one is y dot x. I'm going to switch the order just to get it to look like what we had a minute ago. So we got y dot x, that's the first term, minus beta x dot x equals 0. Solve that, and you're right back where we were. Okay? So I did it by calculus, but you can also just use your intuitions in linear algebra and just think of it as a geometry problem. Okay? But for that, you have to go into this this space that is a very abstract space where the dimensionality is how much data you collect. I mean, normally you think of your data as, well, I had these, in this case, one independent variable, but maybe you have a fancy experiment that's got 5 independent variables and 1 measurement, and whatever. You think of your data as there's 5 numbers plus the 1 number, and that's kind of where you usually plot data, like scatter plots like I started with. But this is a very different way of thinking of your data, thinking, here's all the values that my first independent variable took, that's a vector. Here's all the variables that my other independent variables took, and here's all the values that my measurements took. Okay? So that's a different space where the dimensionality is as big as whatever your patience was in terms of running lots and lots of trials in your experiment. Now, no matter what we do, we end up with this triangle, which takes the amount of y that we had and splits it up into 2 pieces. The amount of y that we account for and the amount of y that we don't account for. So that's written right here. Y has a length, or a squared length, right? And Pythagorean theorem says that the squared length of this hypotenuse is the squared length of this leg plus the squared length of this leg. The squared length of this leg is the squared length of beta x, meaning the thing we tried to account for the data with. So beta opt, the optimal beta, the one that made that a perpendicular, times x has a length squared, which is this, and this is the amount of y that we were never able to account for. It's the irreducible error, the error that we can't fix if all we're allowed to do is stretch the length of x. And so we've partitioned the squared length of our data into 2 pieces, that which we can account for with this linear regression, and that which is left over. Okay? That's just, again, a triangle, right triangle, and it's Pythagoras, but it's also a more abstract concept that we're going to hit many more times this semester. It's a very standard kind of inevitable concept of trying to account for data with some linear combination as best you can, and the way you do it by being as best you can within the realm of what you're allowed to do with your independent variables is to reduce the error to be perpendicular to that which you can achieve with the other, with the degrees of freedom you've got. And so that always leads to this partition of the variation in your data into that which you can account for and that which is error that you can't fix. Okay? So this idea of a partition is going to come back. Okay. So that's linear regression in its simplest form. One predictor, one predicted, and all you have as a degree of freedom is how much of your predictor are you allowed to use. That's beta. So you're allowed to stretch it or shrink it or turn it negative, but you're stuck on that line. That's all you get. Now you may have thought of linear regression as fit a line, whatever line, meaning it doesn't have to go through the origin. But by doing that, that means you have 2 predictors. You have I'm allowed to switch the length of the line, but I'm also allowed to move it away from the origin. We're going to get there probably today, but that already is a multi-dimensional world you're living in because you have more than one predictor. So this was the simplest case of one predictor, one predicted, and one thing that links them. Okay, so let's start moving towards what happens when it's more than one dimension of predictor, regressor. Okay? So suppose I want to account for some data, independent variables, which has lots and lots of values and is written down as a vector. So this is the first data point, the second data point, the third data point. This is my y that I'm trying to predict. But now I'm not just trying to predict it with one regressor, as I was before, one independent variable that I was manipulating in this experiment, but now I got 3. Okay? Or 5 or 4. Right? It's the same problem, but its dimensionality is now increased. Okay? Because I'm going to allow myself to predict y with x1, with x2, with x3, with weighted combinations of them, and the weights are what I get to choose. So I don't just get one value of beta, meaning I live on this line, but I get 3 values of beta. If I had 2, it means I get to live on this line, or combinations between these 2 lines, which means I get to live in a plane. If it's 3, I get to live in a 3-dimensional subspace of this huge dimensional set of data that I've collected. So the data, again, we're living in this abstract space where the number of dimensions is the number of data points you've collected. And here it looks like 1 to 32 from these, what is that? What's that? Stem plots? Is that what they call them? I had to look that up the other day when I changed this slide, in fact.
Lollipop plots.
That's not what MATLAB calls it. It's a reasonable name, but if you're going to do it that way, you should turn them this way. Or maybe not. Anyway, so this is 32 data points were collected. So we're living in this 32-dimensional space. And in this, I can't picture it in this room because it's way beyond 3. But in this 32-dimensional space, there's a subspace of 3 that I'm allowing myself to achieve because I've got these 3 dimensions of predictors. And believe me, you can't, just like with the color matching functions, you can't get this one out of these 2. How do I know that? I generated these by picking random numbers. So there's no way that 2 of them are lined up with a third. Yeah, that has probability 0. Anyway, so that's what we're trying to do. So it all looks the same. I want y to be predicted by a weighted sum of the x's. I get to choose the 3 betas such that I minimize the error. And so this thing here is a weighted combination of these, which means I can turn it into a matrix multiplier. So now I take my x's. I don't remember when I erased my x's. So we've got predictor 1, that's the first stem plot. That's x1. Oh, I don't even want to do that. So, here's x1, 1. Here's x2, 1. Is that right? Yes. x3, 1. Up, xn, 1. That's the first stem plot you have over there on the right. Okay? So that's the first independent variable the n times I did it. x1, 2, x2, 2, xn2. That's the second stem plot, and then we have 3 of them. N3. So now I've taken all my little independent variables and put them as column vectors next to each other, so I've turned it into a matrix. And I have my betas, which I'm now going to call beta 1, beta 2, and beta 3, and make them into a column vector. And the rules of matrix multiply say that I'm going to approximate y1 to yn by the matrix multiply you see there. In other words, beta 1 x11 plus beta 2 x12 plus beta 1 x3 tries to approximate y1. Second one, dot product, tries to approximate the next one. So this is just a shorthand that puts it in the language that we've spent the last, 3 weeks learning. Okay? All right, so we set up a problem, which is now called multivariate regression, because there are multiple variables. And we've said, I'd like to find the best betas. So I could do the calculus thing again. I could take the derivative with respect to beta 1 and set it to 0. Take the derivative symbols around, and I would get the answer. It would be long and ugly, and I am not going to do that to you. It also, by the way, for some of you, pushes beyond the calculus you took, because that's a partial derivative. So that's third semester calculus. Maybe not all of you got there. But one can do that analogous to what I started the class with in terms of solving the one-dimensional problem. But it's really ugly. But there's definitely a linear algebra way of doing it that makes it all clear, which is, in the two-regressor case, do the same thing all over again. So we're living in 3D, but we only have two regressors. Okay, I have three over there, but we're going to simplify it in terms of the picture to get the intuition across. We're going to use the same trick we used with linear algebra. I got regressor number 1, it's a vector in 3D space, or whatever ND space for the n data points I've collected. Whatever it is, I've got x1 and x2, and I'm going to allow myself a beta 1 and a beta 2. So beta 1 is going to take x1 and make it longer or shorter or go back this way. And beta 2 is going to make x2 go longer, shorter, back that way. And allowing myself to use both beta 1 and beta 2 non-zero is going to get me combinations of these two vectors. In other words, it's going to get me somewhere in the plane in which those two vectors sit. Y is pointing off somewhere else. Here pictured as in 3D, but maybe it's in 32D. Doesn't matter. I would like to pick some place in this plane that's as close as possible to Y. And using exactly the same logic as last time, except I can't use a rubber band because it's a plane and not a line. But, a magnet with frictionless. Okay, so I got a magnet stuck to this plane and a rubber band pulling it to Y, and it can slide around frictionlessly trying to get as short as possible. And short is going to be perpendicular, which means I can write the perpendicularity conditions and do linear algebra to solve this problem. Okay? So that's where I'm headed. And that will be the same trick that I used last time, but now there's three things being perpendicular. That says what I just said, that x times beta for all possible betas for two x vectors is a 2D vector space. It's a space of all combinations of them. It's a plane. So that's what that says. Y minus x beta is this error vector right here. And so we're going to try to get as close as possible. When you take beta 1 of this and beta 2 of that, we're going to end up over here. So this is x times the optimal beta. And when you pick the optimal beta, this red line is going to be perpendicular to the plane. Okay? So that's where we're headed. And it's not always a plane because you get a plane for 2 regressors. But for 3 regressors, it's a 3 space. And for 5 regressors, it's a 5 space. So you can't always get the visual. But the intuition is exactly this. Okay, so let me make sure what I want to do right next. Okay, so we're going to solve this 2 different ways. One is, let's just write down perpendicularity and see where it gets us. Okay, so I'm going to redo all of this. How much of the class I get through before I knock down that thing? All right. So when you say that the error vector is perpendicular, so first of all, what's the error vector? You're going to pick a beta such that the error, so the error is y minus x times beta. X is your data matrix, your predictor matrix. Beta are the 3 or however many betas you have. This is the error, and you'd like that to be small. Okay? Now, that is a vector, and you'd like it to be perpendicular to the space defined by your aggressors, which means you'd like it to be perpendicular to not just one of your aggressors, but to all of them. Right? By saying this is perpendicular to the plane, you're saying it's perpendicular to this vector, and it's perpendicular to that vector. Okay? So what you're saying, so now I want to write this to stay consistent. Right. So you want this. So first of all, let's just remember the shapes of things. So x different regressors, the stem plots I had before, and beta is just the same number as these, so for now it's okay? And I would like this, which is a column vector, to be perpendicular to each of these columns, right? Because this is the first regressor I'd like it to be perpendicular to, I'd like it to be good. So I'd like the dot product with these columns. But this thing is already a column vector. So in order to test what's perpendicular to one of these, I'm going to have to take a transpose of somebody. So I'm going to take a transpose of X. So X transpose this thing is this guy, except written the other way. And saying X transpose times this vector, I'm going to be taking this column and multiplying it by the error vector, and I'd like it to be perpendicular. I'd like it to be 0. And I take the second one and multiply it by this. I'd like that to be 0. So I'm going to get a 0 vector, where that vector is just as long as beta is. Okay, I see some scrunched forehead, so I'm going to go through that again, hoping I'm interpreting that some of you are quite with me. Hope it's true. So I'm not wasting your time. So X is, this is stem plot number 1, sitting right here. This is stem plot number 2, sitting right here. These are the things I'm using to predict Y. And beta is how much of each of them I want. Okay? And beta can take on various values, but one beta in particular will optimize things. And the one that optimizes things will give you 0. So this isn't just any beta now, this is beta opt. This is the vector that optimizes this thing. This is the winning vector that when you dot it with your regressors, you get a vector that's as close to Y as possible. Okay? So it's got to be perpendicular to each of the regressors. The regressors are in X. So if I take X transpose, the regressors are now row vectors. This error is a column vector, and it should be perpendicular to every one of those. Which means the dot product, which you'll get from a matrix multiply, because matrix multiplies take the rows of this and dot them with the columns of that, and this thing only has one column. They should be 0 if they're perpendicular. And you get it every time, and you should get a 0. Which, the one thing I did is I put 4 of them here, I don't know why, because I put 3 of them there. So, actually, I really mean 3 zeros. Okay? That's what you should get. Now, this is linear algebra. This is X transpose Y minus X transpose X beta opt equals 0. Just multiply through, which you're allowed to with matrices and vectors and stuff. Okay? And I can move this guy to the other side, which is to say X transpose Y minus equals X transpose X beta opt. Get really close here. All I got to do is take this thing and move it to the other side. How do I do that? What do I multiply both sides by in order to get the guy on the right to go away? I'm hearing the right answer from lots of people. Who said it over there? Okay, so if I multiply both sides by this guy's inverse times this guy, by definition, the identity goes away. And so in other words, I can move it to the other side just like you can in regular arithmetic, by putting its inverse over here. Now, that's a big sleight of hand. And the big sleight of hand is, how do I know I can do this? When can't I do this? I can't do this if there is no inverse. So X transpose X has to have an inverse. How big a matrix is X transpose X? What by what in the example I've been writing on the board? 3 by 3. It's a small guy. When doesn't it have an inverse? Okay, we can go into the SVD, and we're going to be doing that in just a minute, or possibly after the break, depending on how I go. So we can talk about what it looks like when it doesn't have an inverse. But X is your regressors. And you you've just been through an example in color vision where you're not allowed to pick any old primaries. They have to result in color matching functions that give you all color. So here, I have these regressors. They can't just be any regressors. For example, suppose the second regressor and the third regressor were the same exact vector. That would be bad, right? Because that would say x1, x2, x3 don't actually give you a three-dimensional space. They only give you a two-dimensional space. And so if I'm going to say it's a 3 by 3 and I'm going to invert it, you won't be able to anymore. So the fancy word from an actual linear algebra course is to say that these three have to be linearly independent. It says that I can't get a weighted combination of these two and exactly get the third one. Not only can't this one be parallel to either of those, it can't even lie in the plane formed by the other two. Okay? So that's the general idea, is if you're going to do a linear regression with a bunch of regressors, they better be different. If you can give me n regressors, they better be actually spanning n different parts of the space that you're working in, or you're giving me stuff that's redundant. And if you give me stuff that's redundant, you won't be able to do this. Okay? So if you pick good regressors, you can get away with doing this. This inverse will exist, and everything will be hunky-dory. Okay. So we now have an answer to the problem. You give me n regress. You give me 3 regressors, 5 regressors. Something I can't even picture in a much higher dimensional space, and you want to approximate some vector y. Here's what you do. Now it's an ugly expression. Let's see if we can look at it a little bit differently and see what you get. So okay. So suppose we use our tools. So I'm going to leave this answer lying around and get rid of the derivation. And now I'm going to work it another way. Okay? So we're still trying to solve this problem of x being perpendicular, that beta being such that you're all nice and perpendicular. Okay, so let's see, this we do first. Let's figure, yeah. All right. So first of all, let's take x, which is our regressors, 3 of them to maintain consistency, and let's do its SVD. So x is U S B transpose. Okay? We didn't just make up this tool, we're going to use it over and over and over again. All right. So first of all, let's remember what all these shapes are. Okay? So V transpose is in the input space of x. So V transpose is how big? 3 by 3. This guy is a little orthogonal 3 by 3. It takes the independent variables and rotates them. Okay? Now, S has singular values. It has the same shape as x. So S looks big like x does. It's got S1, S2, S3 over here, and the rest is zeros. Remember, the number of rows that we're living in now is this abstract state space. It's the number of trials I collected. It's the number of y's. It's the number of dots on that initial scatter plot that we plotted. Okay, and U is in the output space, so it's n by n, big thing. Okay, U is big thing. Okay, so we have this SVD, and okay. So we would like, okay. So now, funny order, I don't know why I'm tripping, but it's just for the order in which I do this. So give me 2 seconds to get back on my feet again. So using the same close to y as possible. So we're saying we like x times beta to be as close as possible to y. Right? We would like u s v transpose times beta to be as close as possible to y. All right. Now, u s v transpose beta is living in the same space as y. It's an n-dimensional vector. It's pointing somewhere. Y is pointing somewhere. We'd like them to be close. Okay? We're going to try to get them as close as possible. We're going to use the SVD to make it easy. Now, if I take those two vectors, and if they're really close, they're just as close if I rotate them. And in particular, if I rotate them both by U transpose. So if I rotate them by U transpose, I can take this equation right here, multiplying the left by U transpose on both sides, and so I'll have S V transpose beta is approximately equal to U transpose times Y. Okay? So I've just rotated, and I'm doing the problem in a slightly rotated in a new coordinate system. Okay? And we'll call this new vector, U transpose Y, we'll give it a new name. We're going to call it Y star. This taking vectors in a new coordinate system and giving them a name is something that we're going to do a bunch in the next 2 or 3 days. So just warning. We're going to play this game where we move into a new space and give things a new name. All right. Now, and V transpose beta, that's just a rotated beta. Let's give that a name. Let's call that beta star. Now we're trying to solve a new problem, which is S times beta star is as close as possible as I can make it to Y star. Okay? Well, this will turn out to be trivial. Why? Because what's S? S, I already have, is this thing, right? S is S1, S2, S3, and a bunch of zeros. And I got to pick a beta that gets as close to Y star as possible. So let's think about, and so Y star is Y star, 1, Y star 2, it's vector, Y star n. Here's Y star. And I want to put a beta here to get as close as possible. Well, let's think about it. Let's first look at the first dot product we get out of this. We get this row times this thing is going to give me S1 beta. And I'm trying to approximate Y1 star. I don't have to approximate, I get it perfect. Okay, so let's call this beta 1 star. Let's set beta 1 star to be exactly Y1 star over S1.
Why do we create a new, why don't we just use
Because I'm making the problem trivial. Not some fancy matrix multiply with numbers all over the place, but something where the matrix I'm multiplying is diagonal and makes all the math easy.
but Y star is still, for me it's still too,
Oh, we'll get back.
it's still not a thing, for me it's like, it's two things.
It's just we want to know what beta to pick, and we're going to pick beta in a new coordinate system such that the problem is easy, and then we'll go back to the original coordinate system and we'll have our answer. That's the trick. It is a trick. You take the SVD, you get the orthogonal transforms over with so that they're gone, and so that all of a sudden the thing you're trying to do is has only one matrix in it, it's diagonal, it makes the answer easy. And then you go back. That's the outline of what I'm doing. Okay? So we're now in a new space, a beta star, Y star space, and in that space, for the first row, I know what beta 1 star should be. It should be that, because that times this is exactly equal to that. Take the second row, multiply. That just gives me S2 beta star. I'd like it to match Y2 star, which means that beta 2 star should be Y2 star over S2. Third row says that beta 3 star should be Y3 star over S3. So for these first three Y's, Y1 star, Y2 star, and Y3 star, don't just approximate them, I get them perfect. And for all the other y stars, for y4 star through yn star, I'm shit out of luck. Because to get them, I've got 0 times this is 0. I can't fix them. No betas affect them. So all these guys are irreducible error. This is error I can't fix. And all these guys I can get fit perfectly. Remember that error service had this quadratic in n dimensions, and I'm going to go over the geometry of this in a minute. It'll still be an n-dimensional quadratic. It'll be parabola, it'll be paraboloid, or an n-dimensional version of that. And it has a bottom. This is the error as a function of which betas I picked. And even the best beta doesn't fit it perfectly, so that parabola is above 0. So below that parabola is error I can't fix. And what the SVD has done for us, it says, here's the error you can't fix. It's all the dimensions except the first 3. Because you have 3 dimensions of beta. They can fix 3 dimensions of error. And by using the SVD, you've separated those 3 dimensions of error. And you've assigned y1 star to beta 1 star. You've assigned y2 star to beta 2 star. You've totally orthogonalized the problem, such that the stuff you want to fix is trivially fixable, and the stuff that you can't fix, you can recognize. What's the SVD of a diagonal matrix? Itself, with identities on either side. Which is to say, a diagonal matrix, the stuff down here is the null space of the input, right? And the stuff up here is the range space that you can deal with. So the null space is now, the y star space, which is rotated from the original y, is rotated in exactly such a way that the null space is immediately identifiable. It's the error you can't fix, and you know how much its error is. It's the vector length of this stuff, because this stuff you can fix perfectly. Okay? So, I have this solution here, which looks lovely. But now I have a different solution, which doesn't remotely look like it. And I haven't even given you the full solution, I've just told you how to get there. So we now have beta star, and we know what it is. Now if we want to know what beta, we have beta star, this board is getting so messy at this point, I need to make some space. I know what USB is USB of. We go to the left side of the board again. Okay, so what did we just do? We just said that beta star opt is the vector y1 star over s1, y2 star over s2, y3 star over s3. I don't know what it is, but we actually wanted to know beta opt, because that was the original problem. And we defined, don't tell me I erased that part, I did. Okay? We defined beta star to be U transpose times beta. V transpose? V transpose? No, V transpose. No, it can't be U transpose. It has to be V transpose. Why do I not?
Is V transpose beta close to Y?
Yeah, it's V transpose beta, sorry. It's V transpose beta, that's why. You're all right, it's the only thing that shape-wise works. I don't know, I was thinking about moving U to the other side, but U didn't move to the other side to hit beta, it moved to the other side to hit Y. So that was my bad. Anyway, we know that. So how do we get beta from beta star? This is how I get beta star from beta. How do I get beta from beta star? I need to invert that. What's the inverse of V transpose? It's V. Okay? So, in answer to your confusion, we moved our vectors to a new space, saw the solution was trivial, and then we used the inverse transform to get back to the original space. Okay? And we're going to use that trick multiple times, and sometimes it'll be not just one move to a new space, but two moves to a new space. So this trick of recast the problem, put little stars on everything. In a moment, we'll recast the problem, put 2 stars on everything, to think about what happened, and then transform back to see what it looks like in the original space. Okay? So we have a solution to the problem, which is the combination of these things. Now, how do we write that down? First of all, how can we write this as linear algebra? I just wrote out the answer, but I didn't write it as a matrix multiplier, a vector multiplier, or anything like that. How do we think about what we did here? So beta opt is V beta opt star. And then how did we get beta opt star? So it's V times beta opt star, but now I want to see what did we do to get beta opt star? Well, first of all, we did this divide by S1, S2, S3. And second of all, we used that on Y1 star, which wasn't the same as the original Y. So let's put the original Y here. How did we get to Y1 star? We multiplied by U transpose. Right? So this right here, that's Y star. That's how I defined it. Then, what did I do with that Y star? Y star is a nice big vector. Y1 star, Y2 star, Y3 star, blah, 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 blah. Okay? Now, how do I get that to look like divide by these S's? So first of all, what matrix do we have that we have a name for that has 1 over S1 and 1 over S2 and 1 over S3 in it? So S doesn't have an inverse because it's not square, but it does have a pseudo-inverse. So there's a thing called S pound. What's its shape? Is it the same shape as S? Okay, that in your hand has a name, what you're wiggling your fingers to say.
The same size as S transpose.
It has the same size as S transpose. It's got to be something that you can multiply by S that sort of acts like an inverse. So it's got a shape like this, and it's got numbers on the diagonal that are not 0 that I'm going to fill in. What are they? Remember, you inverse what you can. So in S, what can you invert? What can you turn into its inverse? Just the non-zero elements. So you've got 1 over S1, 1 over S2, and 1 over S3, and everything else is 0. So let's put S pound right here. And let's see if the shapes work out. Which they don't exactly. So, we have Y, which was a column vector, n columns. We have U transpose Y. It's a new coordinate system, but it's still an n column vector. We have S pound, which is this big row thing. Okay? And now we're going to multiply it. And when we multiply S pound by this, we're going to get Y1 star over S1. Next row, we're going to get Y2 star over S2. And the next row, we're going to get Y3 star over S3. Exactly what we wanted. And then we're going to transpose that by V to get beta opt. So we have just written the answer. Beta opt equals this. Okay. Now, let's look at what we got here. We have beta opt is, let me just get rid of the parentheses now. We don't need them. Parentheses are needed, so we're getting rid of them. We have beta opt is V S pound U transpose times Y. What is V S pound U transpose? It's pretty familiar and very similar to what we started with. So we had a thing called x. We did an SVD on it, which gave us U, S, V transpose. Now we have V, S pound, U transpose. They're all in the opposite order. They all got inverted, except the middle guy got inverted as much as it could be. So this has a name. It's x pound. It's the pseudo-inverse of x. So we would like we would like beta times y we'd like beta times x to be y. X times beta to be y. So we'd like to multiply both sides by x inverse. X doesn't have an inverse. So we do the best we can, which is use a pseudo-inverse, and declare ourselves done by saying pseudo-inverse times y, x pound times y, is our answer. Beta opt equals x pseudo-inverse y. So we now have two answers. Beta opt equals x pound y, that I got by using the SVD and saying that once you do the first input transform, all of a sudden the answer was obvious, and I wrote it down and then told you what it was. I did it using linear algebra and got this horrible looking expression. These two expressions do not look similar. One's got x pound and one has this big thing. So after the break, because I'm late for the break, I'm going to prove to you that they're the same thing. Now before I go to break, I think there are questions. I've looked at people who are looking a little confused, so I want to unconfuse before we do that. Yep?
What's your criterion for when you can and can't use this linear model for your experiment?
When you can or can't use this.
Linear regression.
That's a question for later in the semester. We're going to talk about that. When is a linear model the right model? When's the wrong model? I'm going to show you some slides later today that begin to talk about that problem, but the general problem is huge, because when I can plot it on a graph, and you see the data points don't look like a straight line, you say, oh yeah, that's a stupid idea for a straight line. But when you're in a 100-dimensional space, you can't look at it to know that, so you need to have some criteria. So that's a topic for a good piece of the semester off and on. I can't answer it just now. But I will answer later today or beginning of next time, fitting something other than a straight line to data, like a quadratic or a cubic or a straight line doesn't go through the origin. I will talk about that. But as to whether you know it's the right model, that's a deeper question. You could spend years on that one.
One thing I was confused by is that there were times when we talked about it being an n-dimensional space, and there were times when we talked about it being a 3-dimensional space based on the number of predictors. And
Right, so sometimes I'm taking x, which is, first predictor, second predictor, third predictor, trying to account for y, which is, so this is n, and so when you think about the columns, they consist of all of your data points that you collected. When you think of the rows, that's the number of predictors you're using to predict things. So I have, for this data point, I have 3 predictors trying to predict one number. So I keep flipping between those two spaces. There's one space which is the 3-dimensional space of your predictors plus the 1-dimensional of the predicted. So that's the way you usually plot your data, and then you get a scatter plot. If you take all that scatter plot and call it a vector, now you're in this very abstract space, which is n-dimensional, and being the number of data points you collected. Okay, let's take 3. Big hand on the 18. Recommends.
So this trick only works with squared error, correct?
Correct. We're going to talk about what happens when you use different error metrics and ways of solving with it. We're not going to fully do that, but in various times this semester, including in a moment. So we're going to mention what happens when you change the metric. I want to finish this metric story. Quadratic metrics are lovely. They're lovely because you can get a closed form solution. You don't have to go looking for the solution. The solution can be written down. So we like squared error metrics because they're nice to work with, but they may not be the metric you want. They may have some bad properties, and we'll talk about those mostly next But first of all, I just want to say that I just solved this problem 2 different ways, and I got what looked like 2 different answers. One of them is beta opt is x's pseudo-inverse, which is written here, and one of them is beta opt is this thing. So they better be the same answer, which means x pseudo-inverse better equal, question mark, x transpose x inverse x transpose. So I'm going to do some symbol pushing just to make sure that we believe those are the same. Now we already, had defined the SVD of x. X is u s v transpose. So I can sub that in here. And we also know that x transpose, when you take the transpose of a product, you just write them all in the opposite order and transpose them all, right? So x transpose is v s transpose u transpose. Right? That's a rule you've learned, and the proof of it's kind of obvious. You've just switched the matrices the other way around, but put them in the opposite order, so the same dot products are happening. And you can do it over and over again, so it's not just for 2 of them in a row, it's for a whole bunch of terms in a row. You can always do that. Okay, so now we can put all those in here. So this thing is x transpose v s transpose u transpose. That's the first guy. This is that. Then we write down u s v transpose. This is that. Put parentheses around that. We need an inverse. And we're going to multiply by x transpose, which is again v s transpose u transpose. This is that. So I've just taken, I want to know whether this is the pseudo-inverse of x, and so I'm taking the thing on the right, and I'm going to apply the SVD and start doing stuff. Okay? So, first stuff we do. What's the immediate thing that makes this simpler? Look at that big, long mess, and what simplifies instantly? Cancel what? U transpose u. U transpose is the inverse of u. U transpose u is the identity. The identity we don't need to write down. So the technical term I use every year is these 2 guys go poof. Okay? That's what we got so far. All right. So now let's right. So let's start taking apart some of the things that we have left. So in the middle here we have S transpose times S. Okay? So S was a big tall guy. S transpose is a long narrow guy. Both of them have S1, S2, S3 in them. And a bunch of zeros. S1, S2, S3. And the shape now is going to be 3 by 3. So just these guys are going to give you a little matrix that's S1 squared, S2 squared, S3 squared. Just doing the matrix multiplied by hand. It's a diagonal, so it's easy. Are we cool with that? Okay. So that's what we've got. Now, this whole thing, and then just to write what's in the parentheses, we've got a V over here and a V transpose over here. Okay? This is a matrix. This parentheses says we would like to take this matrix and invert it. Okay? Well, that's easy. We have the matrices SVD right here. When you have the SVD, the inverse is obvious. You flip the in order and you invert everybody. Right? So I want to take this guy and put him to the -1 power. This guy to the -1 power. Put this guy over here and invert him. Means I need to put a V over here. That's this guy coming over here and inverting. Put this guy over there and invert him, which means put a V transpose over there, and invert the guy in the middle. Inverting the guy in the middle is trivial. It's 1 over S1 squared, 1 over S2 squared, and 1 over S3 squared. Okay? So we've just we've done, now the horrible thing, this inverse is gone. So now we have this times this, times V, S transpose, U transpose. Okay, that's where we're up to so far. Everybody got that? I just did one step. I took the thing, the parenthesized expression, simplified it, and managed to get it inverted. Okay? What's the obvious next step? We have a V transpose V in there. What's the technical term? Poof! Okay. It's getting simpler by the minute. Okay. We have this nice little matrix like this, and then we have S transpose. What's S transpose? S transpose, we've done it before. He's right here. This is S transpose. Okay, so S transpose is sitting right here. S1, S2, S3, and a bunch of zeros. These two matrices in the middle, I can multiply them by hand. Right? They're two diagonal matrices. It's really easy. Right? Because all I'm going to get is this one times that one, this times that one, and the shape's going to be like this. Okay? So now we're going to end up with V transpose, right? It's a V. No, it's a V. There's no transpose there. It's V times the product of these, which I'm going to write down, and times U transpose. Okay? So what's the product of these? It's S1 times 1 over S1 squared. Otherwise known as it's 1 over S1. It's S2 times 1 over S2 squared, otherwise known as 1 over S2. And it's S3 times 1 over S3 squared, otherwise known as 1 over S3, and everything else is 0. Okay? Now we're getting really close. What's this matrix? The middle one. That's S's pseudo-inverse. So we just ended up with V S pound U transpose. Done. They're just two different ways of looking at the same problem. They give you the same answer. Okay? Now, all this was predicated on S being full rank, because I was taking reciprocals of all the singular values. If you have singular error 0, that's more error you can't fix. And that's an indication that your regressors, the columns of X, weren't actually independent of each other. And you will discover that when you do its SVD. You'll find out that it's not full rank. That S doesn't have as much rank as it could. Rank being the number of non-zero S's. That's a fancy word for that. Okay? All right. So we've solved multivariate regression. We've solved it two different ways, and the two different answers are the same. One is this big ugly thing, and one is just multiply y by x's pseudo-inverse. MATLAB, play with it. Prove it to yourself. Take a matrix, calculate its pseudo-inverse. P-inv is the function, as I recall. Or do those matrix multiplies under inverses there on the right. And just assure yourself that you get the same answer. You will. I just proved it. But you can do it yourself and just, hands-on might, glue the memory of this. Okay. Now, where I want to move now is to think about the geometry of the error. So let's develop that. Okay, so what's the error as a function of beta? I showed you a picture of that for the 1D case at the very beginning, right? It was a parabola. There was a beta opt, which got the error to be as small as possible, and as beta moved away from that, the error went up. That was a picture right at the beginning of class. Okay? So it looked like a quadratic. And the formula for error is a quadratic, so of course it's going to look like a quadratic in n-dimensional space, n's the wrong number. I never gave the number of regressors a letter. But let's say we have 3 regressors. It's going to be quadratic in 3 variables because beta's got 3 numbers in it. So as beta moves away from beta up in the various directions it can move, error is going to climb and it's going to be quadratic. That much we know. What's it going to look like? Well, look like I'm going to have to go away from 3 regressors and go down to 2 in order to be able to draw pictures. So now let's deal with 2 regressors and think about what the error looks like. Okay, so what I'm interested in, let's change colors. successor matrix times beta. And we're asking how big is that squared error, because that's the thing we minimize at beta opt. So I want to say, what does this look like as a function of beta? All right? So in order to do that, I'm going to do what I did for the solution. In fact, I'm going to take another step in order to think about what this looks like. So what I did for the solution was the first thing I did is I rotated by V transpose. That's right. This little x here, remember, is U S V transpose. Sorry, that's a U. Can't even read my own handwriting. Rotate by U transpose. My U's and my V's don't look different enough. And that transpose doesn't look like a transpose, it looks like a subscript transpose. Okay, I'm going to do exactly what I did last time. I'm going to multiply this and this by, I'm going to multiply this vector by U transpose, which means I can take this error vector and rotate it some other place. It'll have the same length, it'll have the same squared length. So I'm going to rotate by that. So now our new term is the length of U transpose Y minus S V transpose beta squared. That's what I did a moment ago. I'm just doing it again. And I defined this to be Y star. This is an all reiteration of stuff I did before. And I defined this to be beta star.
So can you repeat what we're trying to do here?
I want to see what the error looks like when you go away from the optimal answer. And I want to eventually see what it looks like in the space in which we're working. But again, when I rotated, everything got simpler, right? Because all of a sudden, the different axes were separate. And I'm going to actually do another step, and I'm going to make it even simpler still. Another one of these arrows. Down here, it'll be obvious what it looks like, and then I'm going to transform back. So I'm going to play the same trick I did a second ago, but now not just to look for beta opt, but to look what the error looks like when you don't use beta opt. Because I want to show what that looks like. Okay? Because that'll be important for kinds of regression we'll talk about next week or next Tuesday or maybe next Thursday. I can't remember the order of topics. Okay?
Can I ask something?
Yes,
what
please.
do you mean when it's not optimal? Like,
What's that?
Like many answers are not optimal.
Correct.
So what are we going
There's
to
a whole space.
Okay.
So we're going to talk about two regressors for the moment. So there's a two-dimensional space of betas. It's a plane. Somewhere is the right answer. When you move away from it, I want to say, how does the error grow? Okay, and I want to find out what it looks like in the space of beta, but I'm already in another space called beta star, and I'm about to go to another space called beta double star. There it's going to be really simple, and then I'm going to transform back to see what it actually looks like. That's what I'm doing. Okay? So this is now, this is Y star minus S beta star squared. Okay? Now, I got this S, which looks like S1, S2, S3, a bunch of zeros. And I got beta 1 star, and beta 2 star, and beta 3 star. Okay? That's this term. So you get, as a result, S1 beta 1 star, S2 beta 2 star. Oh, sorry. That was the old example. I gotta go to the new example. My bad. Thank you. Okay, and the rest are zeros. Okay? Yes, I moved to a two-dimensional beta thing. Thanks for stopping me for putting my foot in further. Okay. So that's one way to write it, and I'm going to write it a different way. I'm going to absorb the s's into beta. I'm going to define a new beta star, so I'm going to define beta double star to be S1 beta 1 star, S2 beta 2 star. For the hell of it. This is not a rotation. I'm stretching one axis by one amount, beta's first axis by one amount, beta's second axis by a different amount. Not a rotation. And then I can replace this by this, 1, 1, 0, 0, and a bunch of zeros, times beta double that'll give you the same answer, right? This times this gives you S1 beta star, and this times this gives you S2 beta star, and then the other ones gives you 0, because it's the same answer. So just taking this product and changing it, changing the coordinate system, but I'm changing it a different way. I'm stretching the axes such that the S matrix is this trivial thing. So now we have this equation, this thing we'd like to take the length of. This equation, say. But we've replaced this with a bunch of zeros, times beta double star. Okay? Now, what do you get out of that? You get y 1 star minus beta 1 double star squared plus y2 star minus beta 2 double star squared. And all the other betas, all the rest of that beta matrix is a bunch of zeros. So then you get, the sum from I equals 3 to n of y I star squared. Okay? That's just writing it out. This is irreducible error. It's error that you can't fix. And this is the error that you can fix if you set beta 2 star equal to beta 2 double star equal to y2 star. And if you set beta 1 double star equal to y1 star, you get that part of the error down to 0. Okay, what is this an equation for? What is the locus of points that have the same error? And in this beta double star space, so now we're in beta double star space. So here's beta 1 double star, here's beta 2 double star, and up here is error. Okay? So at beta double star opt, which is y1 star, y2 star, so if you set beta double star in order to minimize error, by setting beta 1 double star to this and beta 2 double star to that, so let's say that's here. Above that point, so this is beta double star opt. Above that, there's going to be some amount of error. This amount of error. And if I increase beta 1 double star away from its optimal point, it's going to increase quadratically. And if I increase beta 2 away from its thing, that'll increase error quadratically. And the loci of identical error will be what shape? If I want to increase the error by 1, how far away from beta double star opt should I go? In each direction. If I go 1 to the right, the error will go up by 1. If I go 1 to the left, it'll go up by 1. If I go 1 in the beta 2 star double star direction, it'll go up by 1. If I go down in the beta 2 double star, but what if I go on a diagonal? Well, what is this equation right here? It's vector length. So errors will be of length 1 when I go a step 1 away. Squared errors will be of length 1 if I go step 1 away. Squared errors will be 4 if I go length 2 away. In other words, the error surface is going to look like a nice little circular parabola in this space. Okay, you go 1 away, error is going to go up by 1. Error is never 0 because there's irreducible error. That's the sum of y3 squared plus y4 squared double star squared plus y5 double squared squared. That error over here you can never get rid of. And this error you can completely get rid of at the optimal, which is to set this equal to this and this equal to this so there's 0. But as you go away from that point, it will go up like a paraboloid. A parabola spun on its axis. And the error will be the square of the distance. So that's in beta double star space. The error surface is a paraboloid of the obvious shape, which is squared, distance squared away from the optimal beta is your extra error. Okay? So now, we did these two transforms. We rotated, I never wrote an arrow for the other one. That was bad. So we rotated by u, and then we, where did I do it on the board? And then we stretched by S. Where this is what I mean by S, by S1 and S2. Okay, those are the two things that got us to the beta double star space. Okay, so now let's get back to beta space, which is the space in which we are actually trying to do stuff. Okay, so how do we get back? I have beta double star space right here, and I have an error surface that looks like a circular parabola. Okay? In order to get to the beta star space, that's to say go back by this arrow, I'm going to squeeze this axis by S1, and I'm going to squeeze this axis by S2. Those numbers may not be equal to each other. So in this new space, I guess I'll plot it here, beta 1 star and beta 2 star. So in order to go from here to here, I have to squeeze by S1, S2. Because going this way you stretch, so going this way you squeeze. And so, since they're squeezing potentially by different numbers, what used to be circles will now be, there'll be ellipses. Yeah, it's elliptical geometry. There'll be ellipses. Exactly. You take a circle and you stretch one axis differently than the other. And these are coordinate axes. So it'll be an ellipse of some, so it'll be beta star opt is now in a new place because you've squeezed here, you've squeezed here. So there's some place which is beta star opt. And above that, you're going to have an error paraboloid. The level sets will now be ellipses, not circles. Those ellipses will be aligned with the axes, because we haven't rotated anything. We've just stretched the axes. Finally, we want to go back to beta space, which means we want to rotate by U. Rotate by U transpose this way, rotate by U this way. So that means we're going to rotate the betas. The beta stars to get betas back. Which means in this space, so now this is beta 1 and beta 2. So now what used to be an optimal is somewhere else because we've rotated. So I'll write it over here, say. I don't know what the rotation was, I never told you, so I'm just making one up. So we did a rotation. This is now beta opt. Above that is still the same amount of irreducible error. Nothing's changed about amounts of errors. We've just placed them differently. We used to have ellipses here that were parallel to the coordinate axes, but we've now rotated. So now we have errors above this. Again, we have a paraboloid, but now we have errors above this that are ellipses that are not aligned with the coordinate axes. Okay? Now, why am I telling all of this? Because one of the places we're going to head in the coming weeks is suppose you want to do a regression, but the betas aren't allowed to be anything you want. You want to put a constraint on them. So you're not going to necessarily be allowed to go here because the constraint may say, no, I won't let you go there. And we'll talk about various kinds of constraints on betas. So that means you're going to want to be as low on this paraboloid as you can, such that you lie on the sets of betas that I'm allowing you to use. And so this geometry will get you a way to think about that. About how can I be as low as possible, but because you're not letting me use every combination of betas, of those combinations you're allowing me to use, how do I get as low as I can? And so understanding the error surface has this very simple characterization, especially understanding that if you do these two transforms, you go to beta star and then you go to beta double star. Once you get over here, the characterization is obvious. The error circles, the errors are the constant error loci are circles, all centered on the optimal, and they're just increasing size for increasing error. And so you want to hit the first circle you can amongst the choices of beta you're allowed to take. And so that's, I think, literally where we're going next time. So that's why I went through this whole exercise to let you know about the elliptical geometry. So one more slide for today and then we're done. And it's this one. So what's this slide meant to say? So we used quadratic error throughout this. That was our error metric. That was the thing we were trying to minimize. Take the fit y as best as you can such the vector you get with your betas, x times beta, is a vector that's as close to y in the quadratic sense, in the vector length sense, or the squared vector length sense. Same. If you minimize one, you minimize the other. Okay? Now, that's fine, and it's very pleasant because it has a closed form solution, which we've been doing all this time. But suppose you decide to use a different metric. So suppose you decide to use, for example, the absolute value of length to the third power, to the fourth power, to the 1 power, to the 1.5 power. All of those error metrics look like we're taking, you know, the error length, and so here's quadratic, you know, but we could do cubic, or we could do, you know, square root, or, you know, whatever. We could do just the error length. We have these various metrics we could use. And what those do when you spin them around in the beta double star space is they give you a different shape than a parabola. They give you something that's, you know, got steeper sides or shallower sides. But either way, for all those guys, those are functions that are called convex. Definition of convex, I take one place on this error surface, another place on this error surface, I connect them with a straight line, and I'm either on the error surface or above it. And for all of those, if we can't get a closed form solution, what we can do is pick a wrong solution, put a marble there, and watch it roll downhill. You can call functions in MATLAB like fmin search, fmin conv, and fmin whatever, and those are function minimizers, and they start from somewhere and then try and travel downhill. And the point is that if the error metric is convex, there will be one unique minimum, and you can just find it by gradient descent. So you can calculate the derivative where you are, see which direction is downhill, and go that way, and keep doing that over and over again until you get to the bottom. So that's a perfectly nice place to be. It's not as nice as quadratic. So for quadratic, you've got a closed form guaranteed solution. For convex, you can go down. If you have a smooth error metric, smooth meaning it's got a derivative, you can go down, but the error surface, you know, in beta space, so I'll just take one single beta, you know, if you have a smooth error metric, it might do funny things. So there may be a place you want to get to, but if you put a marble here and roll downhill, you may stop there. Okay? So if it's not convex, there may be local minima that are not the global minimum. And so just starting at one place, going to the bottom and quitting is not a good thing. And so methods for searching that space involve searching, starting from lots of places and trying as best you can. But nothing guarantees you to find the minima except for these, you know, stochastic methods like simulated annealing, which can be provable. They will find you the global minimum, but only if you run them so slowly you'll wait until, you know, 50 years from now for your computer to finish. Okay? So as soon as things are bumpy, you have hard work to do, and you cannot necessarily guarantee solutions. And if you're not even smooth, you know, then you're just in a painful place, and we don't want to put you there.
What is the closed form?
Meaning I can write down the math. There's an equation, and you can just call it, and you're done. You can solve for the answer. And not just for the minimum least squares that we're talking about, but for some constrained least squares problems that we're going to get to, I think, next time, if I do so. Now, there's some other questions that came up earlier about what if it's not aligned, etc. That's a deep question that I'm going to start dealing with next time. So we're just started. We've shown you how to get the solution of do least squares fitting, but now we're going to talk about what does it mean, when is it inappropriate, what if you want to put something other than a line, what if the betas aren't allowed to be totally free, but you want to put a constraint on them. So we're going to do variations on the theme, but you've got the math for the theme.